afternoon, everybody. My name is Karan Bhatia. I'm with Google, and I lead the scientific computing efforts for Google Cloud. Thank you for coming. And the title of this session is Scientific Computing with Google Cloud Platform, Experiences from the Trenches in Particle Physics and Earth Sciences. You know, for computational scientists, this is a really exciting time. They have the ability to really leverage almost infinite set of resources. They have the ability to access new processors, new accelerators, and of course, new software tools and platforms to really take all that power and put it at the fingertips of researchers. With Google's global network in 17 regions distributed around the world, it's no wonder that many of the largest scientific projects are looking to leverage the Google Cloud infrastructure for their operations as they scale. We've been working with a number of the different scientific computing projects, including the CERN Atlas team, as they build their infrastructure to enable their scientists to make the next set of scientific breakthroughs. Today we have Mario Lasnig from CERN. He's the Atlas data manager. He'll be here talking about some of the efforts that they have in integrating the Google Cloud infrastructure and services into their existing data and compute systems. But Google Cloud is not just for the largest projects. In an effort to make it accessible to all scientific projects, a few years ago, we made a partnership with the National Science Foundation and provided $3 million in cloud credits for exceptional research proposals in the area of big data. The proposals were reviewed in the same process that National Science Foundation has, and those that were funded had access to Google Cloud credits that they could then, a significant amount of credits that they could use for enabling their science. One of those projects that was funded by this program was the Pangeo project. This was a collaboration between Columbia University, the National Center for Atmospheric Research, and Anaconda, the company that provides a lot of scientific Python tools. The Pangeo project, the focus of that is to build a science platform for Earth scientists to essentially do their science while underneath have all the cloud capabilities with Kubernetes, with Google Cloud Storage, and the other services. Today we have Dr. Matthew Rockland from Anaconda here to show that platform and to explain how they're leveraging Google Cloud in order to build it. I should also point out that Google provides a fairly robust set of services in the free tier. So by signing up with Google Cloud, you get $300 worth of credit, in addition to the core capabilities within the free tier of the services. In addition to that, for academic researchers, if you need more resources than the free tier provides, we have a research credits program where we will provide additional credits for the scientific community as they are building and developing their scientific applications. So please join me in welcoming Dr. Matthew Rockland from Anaconda to talk about the Pangeo project.
Thank you. So hi, everyone. My name is Matthew Rockland. I work for Anaconda. So Anaconda is a for-profit company behind a lot of the open source Python stack. However, today I'm also representing a broader collaboration that includes a lot of scientists and infrastructural institutions, originally Columbia and NCAR, but now sort of a dozen other organizations. So there we go. Yeah, so our goal in this collaboration, this particular collaboration, is to help many scientists analyze large Earth science data sets cheaply. And we'll sort of dive into those few words in a moment. So to give a quick example, this is So this is a video of the Earth's oceans. This is a video of a simulation of the Earth's oceans. This was created on a supercomputer in some institution in Colorado. And it is actually quite scaled down. You can see a lot of interesting detail here. There's the sort of tendrils coming off of Japan there. You can see tides everywhere there's any sort of enclosed area. This is scaled down. This actually is about a 2 petabyte simulation in total. And this kind of data is what oceanographers help them understand how the oceans work, which in turn helps us to understand things like erosion, also things like how heat moves throughout the Earth, which drastically affects things like our climate. So let's move on. So, whoops, no. Okay. So we simulate our planet, like how we saw in the video. We also observe it with things like satellites in the sky or land-based systems. This is critical for many fields like oceanography, also climate science. Those things are more immediately pragmatic. Things like weather prediction. Will there be a hurricane in the next week on the Gulf? Or other systems like agriculture or insurance. Is there going to be a drought next year? How will that affect crops? How will that affect regional instability in Northern Africa? However, once we have those large data sets, I'm back here for a moment. Once we have these large data sets, these are petabytes each for the simulations. NASA has missions that launch somewhere between 1 and tens of petabytes per year coming in at satellite imagery. However, once we have those data sets, we now need to analyze them. Typically, this is done by querying some large data center, pulling off a small bit of data to your local laptop, and then using sort of the natural Python tools like Numpy, Pandas, and Scikit-Learn interactively with Jupyter Notebooks. This is the workflow that we're really focused on. We're focused on the analytics side of these large Earth science data sets. There's some challenges here. The first is that the data sets are different from what normal big data tools are used to. They're large gridded data sets. Imagine the temperature and pressure and wind speed everywhere on the Earth at many different altitudes over time. That data set doesn't fit into a database that's sort of differently structured than what you normally find in most BI tooling. It's very, very natural to use in tools like Numpy, Pandas, or XArray, which are very designed for these sort of gridded data structures. But those tools have traditionally not scaled well. So there's sort of mismatch. We either have scalable big data tools that are designed for tabular data sets, or we have more scientific tools that are designed for small amounts of data. So one solution we use to solve that problem, this is what I particularly work on, is a tool called Dask, which is a library for parallel computing in Python. And Dask imbues other Python libraries like Numpy or like Pandas to produce scalable variants of those libraries. It allows you to scale up the Python ecosystem to sort of the 100 terabyte scale fairly naturally. And we'll see an example of that in a moment. The other challenge we face is increased access. So some people have access to these supercomputers, some people have access to these data centers, but relatively few. You can imagine there might be a graduate student in the Philippines with fairly low resources, both in terms of global connectivity. He can't download the petabytes from Colorado. He also may not have the financial resources to buy all the credits on that. And so we need to create services that allow them to run their computations remotely, bringing the users to the data. This is a problem that many organizations face. We also face it. And we're going to solve that problem with JupyterHub. So people may be familiar with people may be familiar with Jupyter. And JupyterHub allows an administrator to easily provide Jupyter instances to many people within an organization. We're going to see an example of that as well. So I'm going to show an example here of pangeo.pydata.org. And if you want to, you can go to this website now, pangeo.pydata.org. This is a JupyterHub deployment running on Google Cloud Platform. You can sign in with GitHub credentials. And when you sign in, you have the option to create a server, which will provide you your own personal Jupyter Notebook server. Let's skip forward a little bit. As we wait here, Google Cloud Platform is actually spinning up for us some node somewhere on the cloud. That will take a little bit. And we're dropped here into a Jupyter Lab session. So Jupyter Lab is sort of the next generation of the Jupyter Notebook. It has the normal notebook interface on the right that you've seen, but also has things like a file browser. You can open up a terminal. You have a full Linux workstation here. And you can do things like manage your environment with, you can pip install libraries, const install libraries. And this is very, very nice on a personal machine. I use it daily, but it becomes very, very valuable when you're on some remote system. You want to manage that system and keep that persistent. So the combination of Jupyter Lab and JupyterHub we found has been a really good tool to give a variety of people access to a remote system. And again, you can do this now if you go to pangeo.pydata.org. So here, let's do a little bit of science. We're in this notebook, and we're going to import some libraries like Numpy and XArray. And we're going to look at some data stored on Google Cloud Storage. And we're going to look at the sea surface height of a simulation over time. We can see here we've opened up the data with XArray. XArray is sort of a mix of Numpy and Pandas together. We have a bunch of different variables. Look at this variable, the sea level altitude, which is sizable. It's not huge, and it's chunked up into various blocks on Google Cloud Storage. So that data set is too large to work with on a single machine, so we're going to use Dask and Kubernetes to give us more computational power. We're going to ask for, I think, 40 workers. And then, again, we're using the Google Cloud Platform to rapidly scale this user's environment to include now many, many more machines on that same cluster. They're going to connect to that, and they're going to open up some data. So we're going to open up this data set and look at just one day of it. So this is showing us the sea level altitude over time, over the globe, at fairly fine resolution. And so what you can see here, it's a little washed out here, unfortunately. What you can see here is, let's see. Yeah. This is the Earth, and you might be able to see the continents on the left. There's Africa, and there's sort of some wiggles coming off of Africa. And that's the red and the blue are differences in altitude of the oceans. So you can see areas where the ocean might be higher or might be lower. If you live in a low-lying area like the Netherlands or the Philippines, you might be very concerned about that altitude. That data set's around 70 gigabytes. It's not huge, but we can sort of bigger than we'd want to work with our laptop. We're going to do a few computations with that data. We're going to aggregate over spatial dimensions, produce a time average, aggregate over just the longitudes. We have both time and latitude, and then average over the all the spatial dimensions giving time. Before we do the computation, we're going to open up the Dask dashboard so we get a sense of that computation and what's happening. So this is telling us the activity of our cluster as we're running with. So again, Dask is going to give us the ability to scale standard Numpy and Pandas-like workloads onto many machines in a cluster. Here we're defining some of those workloads with the XArray library, which is useful for geosciences. And now we're computing that. So the busy plot on the right shows the activity of all of the cores of our cluster. Every horizontal line corresponds to the activity of one core. And over time, you can see they're working on different things. So one color like the green might correspond to loading data from Google Cloud Storage. Another color like the light green might correspond to computing some aggregation. Red is communication between nodes. And so we've done is we've broken down this large computation into many thousands of small NumPy computations. And then Dask and Kubernetes are working through all of those computations for us. And what that gives us now, we've computed these 3 different data sets. We're going to look at the aggregations all throughout. First, we're going to expand to full screen so we get the full image. And here, so we've taken all the spatial dimensions, and we're now just looking at time. And we can see 2 different things. One, we can see some oscillation seasonally. The sort of Earth breathes a little bit with the oceans. We also see a sort of a standard upward trend. So sea level is rising. And what's really nice here, I'm going to pause this just for a moment. What's really nice here is that we didn't actually need to rely on an agency or trust any organization to give us this analysis. All the raw data was available to us on the cloud. It's publicly available. And we were able to, with our own computations, go to that data set and do that analysis on our own. It sort of removes any sense of politics from the conversation of whether or not sea levels might be rising. So it really democratizes a lot of the ability of anyone on the globe currently to analyze these sorts of data sets. If we take that same analysis and throw in latitude, the slow part here is actually rendering the image, not the computation. So if we throw in latitude, we can see how sea level rise will change over time on the x-axis, but also how it varies over latitude. You can see, for example, there's a sort of a strong difference here at sort of 37 degrees latitude. There's a strong difference, which is actually coincidentally right where we are. So the sea level rise variation increases quite a bit at that latitude. And then here's variation over time. As you can see on sort of the eastern coasts of a lot of land masses, there's a lot of increased variability. You can see a lot of increase and decrease of the sea level rise over time. So again, these are just some examples of how you can today, right now, if you sort of ignore the rest of the talk, you can go run this analysis on your own with open data sets living on Google Cloud, with computation on Google Cloud. This whole computation costs us something like 50 cents. So this workflow is scalable, but it's also very, very familiar. So if you're familiar with the Python ecosystem, the tools like Numpy and Pandas and XArray and Jupyter are very familiar to you. And because of that, this architecture has been redeployed in many different environments. This has had great success. This combination of scaling with Jupyter and scaling with Dask and the rest of the computational ecosystem has been wildly successful, especially in the scientific communities. So this is very commonly deployed on HPC systems, for example, with institutions like NASA or the National Center for Atmospheric Research or the UK Met Office, where they deployed JupyterHub and Dask on an HPC job scheduler, and they run that on some sort of data center. This is great. These institutions already exist. It's a little bit challenging, though, because they all have their own different data sets. And that siloing of data sets can be quite challenging when you have to move large data sets around. Fortunately, the same exact stack also works on the cloud with tools like Kubernetes. And it works on any cloud platform that supports Kubernetes, like Google Cloud Platform. And what's nice here is that because many institutions are all placing their data sets on the cloud, suddenly all these computations become much more universally available. You can start mix and matching. You can combine your oceanographic data sets with your population movement data sets. And it's all publicly available, so it's very pleasant to start combining those things. So just briefly, some successes and some challenges we've run into. So this has been really started as a collaboration between a science group at Columbia, a data infrastructure group at the National Center for Atmospheric Research, and some open source software developers in Anaconda, but it's rapidly spread out to other groups. So many government organizations, and also many different other scientific domains. What I showed up above was useful for geosciences, but it's equally applicable to genomics or to imaging. Those communities have reached out. It's also applicable to many more for-profit enterprises. So Numpy and Pandas are used in geosciences and everywhere else as well. Scale, so scientists are regularly interacting with 100 terabyte data sets. And when I say interact, I don't mean computing on 100 terabyte data sets. I mean, they've opened up a Jupyter notebook, and they're typing out that notebook, and they hit enter, and they expect to get a response back within a minute or so. So they're actually doing interactive analysis with these large, complex data sets at sort of human timescales. And that's really important for the innovation of science. And we're also doing science. So the people at Columbia who originally designed to do this work are doing this work, and they're coming up with new analyses. In the cloud in particular, it's been very nice because auto-scaling has been very helpful to reduce costs without maintenance. We actually don't pay anybody to manage the system that you can play with now. It's up there, it's live, it breaks very infrequently, and it's usually my fault. And it's relatively cheap. These analyses are, because we can scale our clusters up and down, we can burst out to 1,000 machines, and we can go back down again to 0 again, and we can be fairly cheap in that way. This has also been pretty impressive for access. So if you sort of watch people who log in, a lot of them are graduate students, a lot of them are undergraduates, a lot of them aren't in resource-rich countries, and it's been very exciting to see this large-scale analysis be taken out to those other communities. However, there's also a lot of challenges. So we're struggling with interactivity on sort of petabyte scale data sets. So Dask, a sort of underlying parallelism machinery, seems to be struggling to operate interactive timescales for those sizes. Data formats. So the established formats for gridded data, things like HDF5, don't work very well on cloud storage. There are alternatives, but now we have to sort of build consensus among a lot of scientific communities to establish new common data formats designed for infrequent random access. There's a general lack of expertise among the science IT community. There's a ton of people who are well trained to handle HPC clusters, and there's relatively few people in the science community who have sort of the cloud native skill set. And that's some retraining process needs to be done. And then finally, there's resource management. So things like JupyterHub or Kubernetes lack some of the fine-grained user management around software environments, resource limits, data sharing, and governance that are sort of tricky if you want to manage 1,000 users all hammering a cluster with their own particular resource queues. Taking on my open source hat, putting on my enterprise hat, Anaconda Enterprise solved these sorts of problems and actually didn't understand what these problems were before I built a system like this. It was sort of hard to understand all of the pain that goes around stopping the users from breaking the cluster before you have a bunch of users actively trying to break a cluster. So, okay. So that's it from my bit. I'm going to hand it off to Mario in a moment. But give it a try. So you go to pangeo.pydata.org. You can play with that exact same analysis. It should all just work. If you want to learn more, you go to pangeodata.org. If you're an interesting partner, if you want to join in, there's many organizations that come and play with us. And you also get involved. So we're a community organization. We do all of our communication on GitHub, pangeodata/Pangeo. So thank you so much.
Yeah, it works. Okay, hello everyone. My name is Mario Lasnik. I'm with the European Organization for Nuclear Research, commonly known as CERN. Thank you, Karen, for giving me the possibility to speak here to you. And I do this on behalf of the Atlas collaboration. So Atlas is one of the experiments that we host at CERN. Okay, maybe I should stand here and use that. Okay, so just a little introduction. CERN is a particle physics research lab at the border of Switzerland and France, beautiful Lake Geneva. And our accelerator complex is 100 meters underground. You have the Large Hadron Collider, the LHC, 27 kilometers circumference. And you have 4 experiments, 4 detectors attached to the LHC. And we basically make particle beams collide in the center of these detectors. And our experiment is the Atlas one. So this is what an example event looks like. So this is a cross-section of the detector. It's layered like an onion, different types of things that we can measure. Most importantly, the energy deposit over time of the decaying particles. So what we get, the yellow dots that you see are essentially hits in the detector. So you can imagine this is a camera, and it takes pictures every 25 nanoseconds. So that's a lot of data coming out of there. If I'm not mistaken, it's roughly 1.7 petabytes per second. And then we trigger that down in hardware to event sizes of 2 to 8 megabytes in size. So this is just the raw data coming from the detector. But computing at CERN has a quite longer history than that. On the left-hand side, you can see the original machine that Tim Berners-Lee used to create the original technology for the World Wide Web. It's now in our museum. It actually still works. They had an event 2 years ago where they tried it out again. Then we improved a bit, so our data center right now is, I believe, at the 250,000 cores that we provide. 300 petabyte of disk and 200 petabyte of tape. Yes, we still use tape, but eventually all of this is just the infrastructure underneath. What we actually want is plots like that on the right-hand side. This is what the people are actually interested in. And if you're a particle physicist, you can see the Higgs boson in there. You might have to zoom in a bit. Okay, so how do we do the computing for the experiment? We leverage what we call the WLCG, the Worldwide LHC Computing Grid. Now, CERN is not the only sensor providing capabilities. We have 170 data centers all over the world, 40 countries, altogether 800,000 cores, some disk, some tape, and the aggregate network that we can use is roughly 3 terabits. It's a tiered structure, so we have tier 0, which is CERN, and then the large data centers, Brookhaven National Laboratory, Rutherford Appleton Laboratory, all those kinds of very big laboratories are involved. And then we have the tier 2s and tier 3s. Those are universities and laboratories within the national research councils, funding agencies that are attached to the larger data center. It's really a tier structure. And what we do is heterogeneous computing. So our data centers are publicly funded. So it's not like somebody in Spain makes a decision to buy Intel processors and then everybody in the world has to buy exactly the same hardware. No, every single data center have their own funding structure, their own decision-making process. So it's really everybody can do what they want literally, and we have to make sure within the framework of the WLCG to make it work together. And not only that, the data centers not only support the Atlas experiment, but also many different experiments as well, and then pledge to the experiment. The distributed computing project for Atlas takes two concepts, workflow management and data management, merges them together. We basically schedule computational tasks. It's really like a huge batch farm across all those data centers. It interacts with the compute. And the data management is in charge of all the experiment data. And you can see from the curve on the left-hand side that we're approaching 400 petabytes of experiment data there. Now, this includes user output data to detector data, everything. But we also have a very large operations and support team, and without these people, nothing would work. So they do the databases, the monitoring, the analytics for the experiment. Okay, now I would like to quickly touch the data management system because that's where I'm primarily involved in. When we think data management for science, it's really completely different to a business use case. Because the science workflows, as Matt already explained, they are a bit complicated. So what we try to do is we try to have this global namespace that we can federate across all the different storage systems that the countries provide. We need to control and account the data and users. We need to have some policies and rules on the data. We have to transfer data between the data centers. We have to make sure that when the jobs access the data that it's available, we can do popularity-based things, replication, caching, all those kinds of things. And then we also have to interact with all the other systems that actually need the data. So the system is called Rucio, and this is the one that we're actually integrated with the Google Cloud Platform. So I think in the interest of time, I will just skip to the next slide, because that's actually where it gets interesting. When we do orchestrated storage-to-storage transfers, so basically copying a couple of petabytes from France to the United States, we have to hop through many different research networks. And as you can see, we do roughly 5 petabytes of transfers per week, all of different types of activities. But when the data is there, the actual jobs need to do something with them. So the job I/O we get per week is much, much higher than the actual orchestrated activities. So the other one we can schedule. We have a list of data that we want to transfer. We know roughly a month in advance which data we actually want to move. But when we have users accessing it, this is completely chaotic. And as Matt showed, you push a button and suddenly you try to work through a petabyte sample of data. And we have to make sure that this is properly orchestrated, not only worldwide, but also at the lower level with the storage systems. Okay, so that looks actually quite well and it works. So what is the problem? And the problem you can see here on this plot on the left-hand side, that is the prediction of the amount of data that we will need. And you'll see there's a very big jump in 2025. This is when we will get the high luminosity upgrade to the Large Hadron Collider. So from roughly 1 exabyte of data, we will jump up to 4 and more exabytes of data. And already now at 400 petabytes, we're having quite a bit of trouble getting the job I/O working. So this data deluge, this is not only a problem for the LHC. We see this across many fields of science. And the main problem there is that, of course, storage continues to be the major cost factor. The science output rate exceeds the infrastructure growth rate at any possible rate. I mean, you can't leverage so much taxes that you build many more science centers. So we call these tactical resources. It's like we want to use these excess resources that are available in the world. And so Atlas and Google joined forces to start the Data Ocean R&D project. There's this data lake concept that's very much used in business, so we tried to give it a funny spin and just call it a data ocean just to make it bigger. There's absolutely no meaning behind this, right? So what we tried to do is we wanted to make it easy for the science users in the experiment to benefit from what Google Cloud can provide us. But on the other hand, we also wanted to learn from Google how they do their things. So we wanted to evaluate, adopt, and benefit from the novel technologies that are available on the market. So at the supercomputing conference last year in Denver, we had our first meeting. And we started out with a large sheet of paper and started to draw potential scenarios, what we could do. And we ended up with our first white paper on this. So the first use cases that we wanted to do is to ensure user analysis. Imagine on the WLCG, your job runs, it produces output, it writes it somewhere in the world. But for example, it ends up in a data center in a remote country with not so good network, and the only administrator there is a PhD student on 5% time. Data center goes down, you have to wait 3 days to get your job output data. That is clearly not what you want. So with Google Cloud Platform, we would be able to get 100% output availability by making an additional copy on the cloud. Also, we should be able to overflow the CPU to cloud compute. Then the other thing that we wanted to test is the data placement, replication, and popularity. I think we really want to dynamically expand the storage capacity, use the additional network that Google provides us between our national research networks. For example, we can inject data in our data centers in Amsterdam and have it use the Google network to move it to the US without having to rely on our own research networks. And then, of course, within the Google network, try to replicate it even more. And the third topic that we would like to test is to get the internal data formats that we use for the job I/O itself. What we use is if you know HDF5, it's a data format using trees. We use the root system for this. So what we want to rip it apart into its constituents and try to figure out what would happen if we don't use files. So eventually we would end up with a couple trillion events that we need to process. So we're clearly not there yet. So we wanted to do some cloud-based marshalling of events from this. Okay, so how do we get data into Google Cloud Storage? This is the necessary first step, but the LHC is running, so we can't just shut it down and do this. So we had to integrate this transparently and on the fly, because downtimes while the LHC is running are very, very costly. So what we try to do is to make GCS just another data center within the WLCG. So this means within all the existing heterogeneous data centers that we had to make sure it supports all the data policies, it supports the user data access with the authorization and authentication, it must support the existing protocols that we use, and also the existing tool chain that we have. So this was quite a bit of development effort. So we started with S3 because we had full stack support from top to the bottom. And you can see in the center, there's the Rucio data management system that connects the WLCG sites and the Google Cloud Storage. But then we quickly figured out that if we continue to use S3 as our primary data access protocol, that we're running into some serious problems, because this one is rate limited on the storage sites. And really what's the major problem is that the key distribution is problematic. So imagine we have our credentials to access Google Cloud Storage and we start to hand it out to our users, and somebody decides to just run through a couple of petabytes of data. We would rack up a bill that we could never fund. So what we decided to do is we say, okay, we don't use the compatibility layer with S3. We move to Google Cloud Platform native client-side URLs. And with that, we have complete control over the integration. So these first movements we did, they were quite manually slow and tedious due to S3, but with the signed URL support, this basically allowed us to use the Google Cloud Platform like any other web DAV storage, which was really cool. And then we used this to do user analysis input to the European West 1 and the US East 1 storage areas in GCP. And what happened was that we maxed out the intermediate throughput and started to overload the storage from the WLCG because we couldn't even inject it fast enough into Google Storage. So we were quite happy with that. When you have your data in, you want to compute. And we have a system built in collaboration with the University of Texas Arlington and Brookhaven National Laboratory that is called Panda, and it has a component called the harvester. So what the harvester does is it basically is a real-time view on the capabilities of your cloud, and it tells you how much usage you have from the experiment point of view, not from the infrastructure point of view, and what is the integration with the cloud costs that we actually have. So we continuously fire up virtual machines with the actual computational pilots in them. We can poll the VM states, we can shut them down when necessary, and we thus have the compute engine completely integrated into our batch workflow. And at the bottom, the Rucio system takes care of moving the data from the WLCG systems, storage systems into the Google Cloud Storage through the orchestrated transfers. So we started with Atlas simulation jobs. When I said at the beginning that we get a lot of data out of the detector, we even get more data from our simulation. I think the split is something 30% to 70%. So 70% is just pure simulated data. Now what we need to do is we need to run these simulations on the Google Compute Engine clusters and read the I/O from the CERN storage. That was the first step. We wanted to show that we can run the compute on Google, but accessing the data at CERN. And then we moved on to also use the I/O from Google Compute. In the meantime, we decided that we could try to profit from the preemptible virtual machines. And you can see on the left-hand side of the plot, we use the normal VMs that are available on GCE, and then we switch to preemptible VMs. So this basically means that the infrastructure can take out the VM underneath you. However, if you do this, you gain a lot of dollars per event. So this was a very positive experience there. So the Atlas analysis also works. The simulation case was just the first step. We can use GCE with I/O from CERN, with I/O from GCS, and it's completely and fully automated. So the physicists themselves don't even know that their jobs are running on Google or that the data is used from Google. So what is the take-home message? The science workflows and the software that we use are complex and complicated to a point where we can't just go ahead and change things, because we need to have repeatable experiments. So if we decide to make an addition like enabling support for a commercial cloud provider, we have to make sure that this is done in a very, very conservative way. So all these workflows have to transparently integrate these providers. But then we come to the next step, because the scientists themselves are starting to get cautious. To scientists, the data is the most precious resource. They literally don't care about the infrastructure and where it runs. But if you tell them, we're taking all your data, that is basically your livelihood, and we're putting it on a commercial company, and it's not on publicly funded and science infrastructure, they start to get very, very cautious. So what we are trying to do here is we're trying to win the scientists, we're basically trying to win ourselves over by providing ourselves tools to use the commercial platforms in a way that makes sense to us. So we can allow our existing science software to run transparently against a commercial provider, while at the same time keeping complete control of the data. So for us, really the important part was to have a data management system to be able to do that. So imagine you're a science community. You're not on the scale of Atlas. You're maybe 10 people, 5 to 10 people, and you decide, okay, I have access to my university storage cluster, but I would really like to get some capability from Google Storage completely integrated into my workflow. You can use our Rucio system to do this. You can use the Panda and Harvester system to do this. So we really give you the possibility here to integrate your existing on-premise capabilities with the commercial cloud providers and give you as a science customer full control over all your collaborations data. So Atlas and Google are committed to a long-term collaboration. This is not a one-term thing. So we're really looking forward to scaling out even more. We have many more experiments that are deploying the same tools, and we are giving them essentially the capability for free to hook into the commercial cloud providers and use it as part of their science workflows. And with that, I'm at the end. Thank you.